Introducing me. Assalamu alaikum everyone. This is Tariq Adnan and I am today presenting my thesis work. The title of my thesis is Fast, Scalable and Geo-Distributed PC Algorithm for Tall and Wide Big Data Analytics, and my thesis supervisor is Dr. Mohammad Abdul Adnan sir. Let's have a look at the outline of our presentation. We will start with showing some motivation behind our work. Then we will define the problem formally. Then after showing a brief technical overview, we will discuss the state-of-the-art methods of PCA with their shortcomings. After that, we will describe the techniques we will impose to solve our problems. Then we will analyze our algorithms with their relevant complexities. Then we will demonstrate the experimental setup that we employ to carry out our experiments. And finally, we will conclude the presentation by showing our experimental evaluation. So let's start with some motivation behind our work. Assume that we have a data set where the number of rows is in thousands and the number of columns is in hundreds. If we want to run any machine learning model on this data set, we can do it without any issue. But when the dimension of the data become higher that any machine learning model might fail to run for such higher dimension, then we have a simple way out. We have a good old friend PCA, that means the principal component analysis, which can reduce the dimension of the higher dimensional data and make our life easier. But life is not that much easy because the dimension of the data never stops growing, and eventually it becomes so large that even PCA algorithms fail to help with its dimensionality reduction feature. That means the existing PCA algorithms are not scalable enough to handle arbitrarily large dimensional datasets. Now let's make the scenario more complicated. What will happen if such data is distributed into different geographic locations? No way, our good old friend PCA is totally confused now because there is no PCA algorithm that can address such geo-distributed datasets. So let's see if we can help them out and do something to resolve all these limitations. We will formally define our problem after going through some terminologies. First of all, we will define the term tall and wide big data. For this kind of data, both the number of rows and the number of columns are very high. They can be in millions or even can be in billions. They are not suitable enough to fit into various machine learning models, and they need higher amount of processing. In recent years, most of the companies are storing their data at different geographic locations, mainly closer to the end users, so that the access time gets faster. In this way, the data privacy can also be ensured at some extent. The problem is that in this kind of setup, we do not have any centralized view of the data. Now, PCA is a very popular method for dimensionality reduction. It finds the direction of the maximum variance, that means the principal components. The most important thing of PCA is that it compromises very little of the data information, while it can give us the advantage of having a lower dimensional data. Finally, the scalability of an algorithm. This kind of algorithms can tune itself with the workload so that the performance is never compromised. If we want to define a scalable algorithm for PCA, then we can say that it should be capable of handling datasets with an arbitrary number of dimensions under the same infrastructure and of course with the same efficient performance. So what are the associated challenges in our work? First of all, the existing PCA algorithms are scalable only up to some extent, and they cannot handle arbitrarily large dimensional datasets. We have found that for two very popular PCA methods, the amount of memory uses per machine were 37 gigabytes and almost 75 gigabytes, even for computing only 100 principal components, and also from a dataset which is not that much higher dimensional. In fact, with the increment of data dimension, the amount of intermediate data becomes so large that eventually they face out of memory error for the tall and wide big data that we have defined earlier. And of course, for solving the scalability issue, we cannot throw unlimited hardware because that will eventually saturate tomorrow or the day after. Moreover, to ensure faster data access to the end users, data is now geographically distributed. And unfortunately, none of the PCA algorithms can work on such geo-distributed data. One way around is to gather all the data sets in a central location and then execute the existing non-geo-distributed algorithm on this centralized data. but more problems in that because inter-region transmission is costly and many countries even prohibit the passing of raw data across their own national boundary. So now we can formally define our problem. Basically, we need a PCA technique that is scalable. I mean, that can handle our defined tall and wide big data without incurring any memory overflow error. And also it has to be capable of performing a communicational efficient calculation in case of an geo-distributed environment. Now let's have a brief look at our contribution to overcome the memory overflow error. We have introduced a novel block division method for probabilistic PCA, which is up to 42 times faster and almost at least 10 times more scalable than the state-of-the-art methods of PCA. We have also designed our PCA algorithm in a geo-distributed manner, and it provides a communicational efficient solution by passing only the parameter and minimizing the idle times. It also provides almost 3 times improved running time. We have named our algorithm as TallnWide, and we have provided a geo-distributed implementation on a Spark of it. Here is a brief technical background. Throughout this presentation, we will use these notations. Capital Y is our data. Capital N is the number of rows. Capital D is the number of columns, or we can simply refer to as our data dimension. Smaller d is the number of principal components, or we can say our target dimension. Mu is the mean vector, and YC is the mean center data. Principal components can be computed using multiple techniques, like it can be derived by performing the eigenvalue decomposition of this covariance matrix. In this way, this matrix U will be containing our principal components as its columns. Then the singular value decomposition of the data matrix, which will provide us the principal components in this matrix phi. Then the stochastic singular value decomposition, which starts with sketching the data matrix, and then it performs the keyword decomposition of the sketched matrix in order to generate an intermediate state Q. And finally, it performs SVD of the multiplied version of the transpose of the previously generated Q and the data matrix Y. Also, we have the probabilistic approach of PCA, which provides some extra advantages such as the lossy data compression, feature extraction, and data visualization, etc. Let's have a look at the state-of-the-art methods of PCA. And the first one is the MLNet PCA, which is an EVD-based technique. Then the SSVD-based MEHUT PCA. The distributed PCA and K-means clustering is a work similar to the MLNet PCA, which computes principal components of the local data first and then estimates the global covariance matrix from them. And eventually, it uses EVD of the global covariance matrix to compute the global principal components. Then the SPCA, which is a PPCA-based approach. And finally, SS-Sketch PCA, which is a very recent work of Dr. Adnan sir, which is more scalable than the previously mentioned methods. However, it fails to cope up with the increasing data dimension. The common features of all the PCA libraries are, most of them are built on Spark, which is a very popular memory-based distributed framework. All of these PCA methods suffer from a scalability issue. The space complexity is very high, and as the dimension of the data increases, they face out of memory error. Also, none of them offer any geo-distributed implementation. Now we have come to the main part of this presentation. We will discuss the approach of our solution method. First of all, in order to mitigate the scalability issue, we have introduced a novel block division method that will divide our PCA parameter W horizontally into multiple manageable blocks, and consequently our data matrix Y will be divided vertically into blocks of the same number. That means whatever the dimension of the data, we will always be working with a smaller block of the data Y and the parameter W, and it will reduce the amount of intermediate data generation, and eventually it can prevent the memory overflow error. But such a splitting is not that much trivial, and we have found that PPCA is a very promising candidate in this matter. In fact, we faced a dead end while we were trying to incorporate block division in other techniques like the EVD or SSVD, because these methods need some component to be kept as a whole during the total computational time, which does not allow us to split their computation. We also had to reduce our algorithmic steps into simple matrix or matrix vector operations in order to make sure that no extra overhead is introduced because of this block division. Here is a brief technical detail of PPCA, which is an example of Gaussian linear model. It tries to correlate the observed variable y with the linear transformation of the latent variable x using a PCA parameter w. Given that we have a fixed model parameter w and a fixed variance ss, then the probability of the latent variable to be x, given that y is our observed variable, can easily be computed by using the linear matrix projection method, and the resulting density also follows normal Gaussian normal distribution. Here is an expectation maximization algorithm of PPCA. Such algorithm starts with a random selection of our PCA parameter W. At each iteration, in the expectation steps, several intermediate data like the M, the X, the XTX, or the YTX are generated. And finally, in the maximization steps, these intermediate data are utilized to generate a new W and a new variance. In our research, we have taken the advantage of the zero noise model PPCA. That means we have considered the noise to be zero, and it turned out to provide us with some extra advantages. So with the zero noise model, all the noise involving steps are eliminated and the algorithmic steps become simpler. In the evaluation part, we will demonstrate that the loss in accuracy due to this zero noise model is negligible, considering the advantages provided by our method. Here is a formal proof that this zero noise model can also provide our desired PCA parameter W without any significant loss. This proof has been provided by Sam Ruiz, and his article is referred at the bottom of the slide. Now, here is some terms and notations that we will use to discuss our algorithms throughout the upcoming part. Capital S is the number of geo-distributed data centers. Smaller d is our target dimension. Capital NS is the number of rows of the data residing in the data center number S. Capital I is the block division, number of block division. Capital DI is the number of columns of the block number I of our data. YS is the data set residing at the data center number S. In our work, we have used two notations. This one to represent the vertical stacking of the data, and this one to represent the horizontal stacking of the data. That means our data is initially vertically stacked in each of the data centers, and then they are horizontally stacked across all the S data centers. Mu is our mean vector over columns. WK, capital WK is the principal component parameter of iteration K at each of the data centers. All the I blocks of this parameter W are stacked horizontally in order to form the overall W. Then capital X is the latent variable, which is horizontally stacked over all the S data centers. Now, here is our algorithmic steps. We are proposing a generalized framework that can be applied on any datasets, whether it is geo-distributed or not. That is why the algorithmic steps are shown in a geo-distributed manner. Similar to the other PCA algorithms, we are also proposing an iterative algorithm. So the algorithm starts from a random selection of W, and at each iteration, a new W will be generated until it reaches to a convergence. Firstly, by using the partial blocks of W from the previous iteration, we will generate an intermediate data M redundantly at each of the data centers. Then, in a similar fashion, partial Z will be generated at each of the data centers using its own version of the data blocks and the corresponding block of the previous W. And then, using its own version of Z, each data center will generate a partial ZTZ of its own. And all these partial ZTZs will be geo-accumulated to generate the accumulated ZTZ. And the accumulated ZTZ along with the previously generated M will be used to generate our desired intermediate data XTX. Finally, when we have all our intermediate data ready, all this intermediate data like the M and XTX, the Z, and also the data matrix will be used to generate a new version of W for the new iteration. These all the partial Ws will be generated at each of the data centers. Now, from this equation, we can clearly observe that the partial results of W that are generated at each of the data centers will require a geo-distributed accumulation. Now, we will demonstrate how we do this accumulation task efficiently. This current order is a trivial approach which generates all the blocks of W sequentially. That means the initial block, then an intermediate block, and the final block. After that, it will perform the geo-accumulation of these blocks sequentially again. But in this method, the amount of network idle time and CPU idle time is very high. And of course, this is not a very smart approach. Actually, we targeted to maximize the parallelism between the geo-accumulation of any block and the generation of the further blocks. That is why we decided on this efficient order. That means as soon as any block is generated, it will be sent for geo-accumulation. And at the same time, the generation of the next block will be started. In this way, there will be a significant reduction in the idle times. The task of accumulation and redistribution are carried out by a central data center. Therefore, if we can identify an ideal central data center for this task, then the accumulation time will be reduced, and thus the overall idle times can be reduced by a more margin. If capital B represents the bandwidth matrix among our geo-distributed data centers, then using this formula at the bottom, we can find out an ideal data center that can be used and as the central data center to carry out the task of accumulation and also the redistribution of the partial blocks and the aggregated result. Now we will show the advantage of using zero noise model PPCA over the conventional one. Let us consider the equations for calculating the noise SS in the conventional PPCA. Among these equations, the calculation of the SS3 is the most complicated one, and it will look like this if we convert it into block division approach. We can clearly see that the calculation of SS3 for iteration number k is dependent on the entirely accumulated PCA parameter W of the next iteration. I mean, for the iteration number k plus 1. These will unnecessarily complicate the computation and introduce interdependency between the steps and reduce the scope of parallelism. To illustrate, let us contrast the dependency diagrams of our zero noise model PPCA and the conventional PPCA. Undoubtedly, our one is the simpler one, and then the main conventional one, thanks to the simplicity of the zero noise model PPCA. Now let us explain a bit of our algorithm with its complexities. This is our main algorithm, TallnWide. And the steps are very aligned with what we have described earlier. At the very first step, it produces a random Gaussian matrix of size capital D into small d from a given set. These will be used as the random selection of the initial PCA parameter W. We want to start from the same random state at each of the data centers. That is why we have to send the same seed to each of them, and it will require a communicational complexity of order of 1. Then this algorithm will perform the task of generating various intermediate data and their required geo-accumulation. And finally, it will generate all the new versions of the I partial blocks of our PCA parameter W, and it will also perform their corresponding geo-accumulation. Now, at each of the line, the required computational space and communicational complexities are shown. Now let's find out the major computational cost at each iteration. It involves in the generation of the partial Z and the partial blocks of our PCA parameter W. And this runtime complexity is related to the number of non-zero elements of the data of that particular data center and the smaller d. And this is the overall running time complexity of our TallnWide algorithm. On the other hand, the accumulation of the partial block of W dominates others. That is why the communicational complexity is order of capital Di into small d. The maximum space complexity is the storage of each block of our PCA parameter W. That means similar to the previous one, the space complexity is also capital Di into small d. Here is another algorithm of geo-distributed accumulation. It is a very straightforward algorithm, and for time constraint, we are omitting the detailing. Finally, here is a comparison of the complexities among our comparing methods. As other methods are not geo-distributed, we only compare time and space complexities of TallnWide in this table. Note that we do not calculate noise, and our calculation only involves a smaller sized block of the PCA parameter W. That is why we reduce the constant factors in computational time by a significant fraction. Also, because of the block division approach, our space complexity is less than others, and consequently, we do not face any out-of-memory error. Now we have come to the experimental setup. Here are the 5 methods that we are going to compare in our evaluation section. Our implemented TallnWide will be evaluated against the SPCA, MAHUT PCA, MLD PCA, and SSKetch PCA. We have 5 real datasets. First of all, the PubMed, which is a medical dataset, we are having a 8.2 million of number of rows and 141,000 of columns. The Amazon product rating dataset has 21 million of users and almost 10 millions of products. The largest datasets we have used is the Twitter social network dataset, which has 61 million of users as its rows and columns. All these three datasets are sparse dataset. Also, we have kept one dense dataset, the shift feature, in order to assess how our method responds to such dense data. We have also introduced another dataset, the fashion MNIST, which contains 60,000 grayscale image of various fashion elements. We will conduct our experiments on a single cluster standalone mode with one master and multiple slaves. For that, here is the cluster configuration. We created Amazon EMR cluster on EC2 cloud, and then to imitate a geo-distributed environment, we created clusters at different AWS regions. So during the computation, during the generation of the partial results, the communication will be inside each of the clusters, and during the accumulation time, the masters will communicate among themselves. We chose 3 different regions with 5 different zones and created a cluster of 1 master and 2 slaves at each of the zones with this configuration. Here is the bandwidth matrix of our data centers at different geographic locations. As evaluation metrics of the standalone mode, we use the time requirement to reach a desired convergence rate, the scalability, the size of the intermediate data. We also observed the effect of block division on scalability and running times. For geo-distributed environment, our main focus was to minimize the utilization of cross data center bandwidth. We also examined the running times among various possible accumulation techniques. And this is the convergence criteria of our algorithm TallnWide. Now we have reached to our evaluation part. First, we will show the experimental outcome for the standalone mode on a single cluster, on a single data center. First of all, we will show that our method is identifying the correct principal components. Let us have a look at these figures. This figure of A is visualized from the original fashion dataset. We can clearly see that it contains an image of a shoe, which is a fashion element. Now, these 4 figures are drawn from the data projected on the direction of the top 10 principal components. The principal components of figure B were found by using MLP PCA, by BUET PCA for figure C, by SPCA for figure D, and finally the figure of A is found by projecting the data on the top 10 principal components found by our method TallnWide. We can observe that all these 4 figures drawn from the projected data are similar. That means they are projected on the same principal components. Here is another similar example, and we can clearly see that the reconstructed data are similar for the principal components generated by all our comparing methods. We can see for the actual reconstruction error, TallnWide is providing a slightly higher error rate. However, the maximum reconstruction error is around just 1%. Clearly, it is still within a well tolerance, and such a small amount of compromise in accuracy is acceptable since we are providing a highly scalable geo-distributed algorithm. Now let's see at the amount of the variance explained by the top 10 principal components identified by these 4 comparing methods. We can clearly see that the total variance covered by our principal components are similar to the ones by the state of the arts. For some cases, like this one, the Amazon rating dataset, they start with a slightly lower values, but eventually they catch up as the number of principal components increases. And in summary, they are almost 99% similar with respect to the amount of variance covered if we compare them against the state-of-the-art methods. Now we will show the impact of the number of blocks on our evaluation method, on our evaluation. Note that we determine the number of blocks dynamically by measuring the available memory using this formula. Here, rho is the tuning parameter to determine the effective block number. Our goal was to minimize the number of blocks as much as possible in order to keep the overhead minimum. But at the same time, we had to ensure that the block size stays manageable so that no memory overflow error can occur. In our observation, rho equal 30 yields the best result. So we have set this value for our algorithm TallnWide. Now we show that TallnWide takes less time for convergence. This graph is drawn by showing the running times of our comparing methods to converge to 5% tolerance for PubMed dataset. We can observe that TallnWide takes the least amount of time and it provides up to 37 times improvement in running time. Now, this table shows the per iteration running times for each of our comparing methods while they are executed on each of our considering datasets in order to identify the top 10 principal components. A visually better understandable figure is shown in this bar chart. We can clearly see that for the higher dimensional datasets like the Amazon rating, the subset of Twitter dataset, and the full Twitter dataset, all the state-of-the-art method were failed to run on them. But TallnWide was successful and TallnWide was successful to generate the results. On the other hand, for the datasets that can be handled by all the comparing methods, TallnWide is faster and it provides up to 42 times improvement in running time. Now we come to the scalability. Here we have increased the data dimension and observed the utilization in memory. We can see that for other methods, they are scalable up to a certain dimension, where TallnWide can, with the merit of its block division method, can keep the memory utilization in control. And in summary, we are almost at least 10 times more scalable than the state-of-the-art method. Finally, the amount of intermediate data generated during the computational time. This has been hugely reduced in TallnWide, and this is the main contributing merit to overcome the memory overflow error and to provide the higher scalability. Now we have come to the evaluation of our experiments on a geo-distributed environment. Here are the three candidate solutions to do the accumulation task. First of all, the G-Spark, which is a naive centralized approach. It creates a single cluster with all the 15 instances at different geographic locations. And the bad side is it demands to pass the raw data across the regions. Then the GHDFS, which overcomes the requirement of passing the raw data. It creates 5 different clusters at 5 different regions. And also we have a dedicated cluster consisting with the masters in order to carry out the task of accumulation. All of the instances are connected to a central HDFS where the partial results can be stored and also can be retrieved from. Finally, our TallnWide accumulation strategy, which requires neither any raw data passing nor any central file system. It is a simple procedure where the masters can communicate among themselves through SSH in order to pass the partial results and redistribute the accumulated result. We also elected one data center as the central data center in order to carry out the accumulation task. Here is a statistic of the running times to finish a single iteration using our different accumulation strategies. Clearly, TallnWide is faster with almost 3 times improvement in running time. Finally, we show the merit of selecting the ideal central data center for accumulation. That means the third approach in this figure, which theoretically improves the overall running time. From this bandwidth matrix, using this formula that we have already shown in previous slides, we can clearly see that Oregon 2 theoretically should be the ideal data center. And also it was justified empirically because Oregon 2 provides the best result when it is selected as the central data center. So in summary, if we summarize in our research, we have proposed a new algorithm, TallnWide, to meet the challenges of the geo-distributed TallnWide big data. We have derived a block division method for zero noise model PPCA, which can overcome the memory overflow error, which is 10 times more scalable than the state of the art and also 42 times faster. Also, we have provided some optimization in accumulation process, which yields almost 3 times better performance in a geo-distributed environment. In future, we plan to provide a formula to determine the optimum block number. We also plan to perturb the values of the parameters so that the privacy can be preserved in a better manner. Our Spark implementation code, along with a proper documentation of the setup, is publicly available on this GitHub link. There has been a publication based on this work. An article has been published recently in the 98th volume of Information Systems, which is an Elsevier journal on data analytics. So thank you all for your patience. That was all from my side. I would like to answer all your queries.